Hassan's Maths channel, and I'm now answering question number 7 from the October-November 2024 Cambridge 9709 Mechanics Paper 4 Variant 2. And this question is a question which is referring to inclined planes, friction, and so I'm going to go through, I think 7a is all about inclined planes and friction. So I'm going to go through this question in a bit of detail to make sure everyone understands the concept properly and some of these modeling assumptions that I mentioned, so that people understand what they mean. So it says 2 particles A and B of masses 0.2 kilograms and 0.3 kilograms respectively are attached to the ends of a light inextensible string. So what does the word light imply? Well, the word light implies that we can ignore the mass of the string, so we don't consider its weight. And we also, from the word light, what we assume also is that the tension throughout the string is the same in every part of the string. So at the top here and the bottom here, the tensions are the same, because there's no, like, for example, up here, it won't be carrying the weight of the string that's below it, just the weight of the mass below it. The weight of the string is not, going to be carried by any part of the string above or below. So therefore, the tension in the string in every section is going to be the same. At the top and the bottom here, the top of the bottom here will be the same. All right. Then it says the string passes over a small fixed smooth pulley. Now, the fact that the pulley is smooth means basically there's no friction in the pulley, which implies that the tension on either side of it in the string will be the same. Okay. And the word inextensible, by the way, also the string being inextensible, meaning it doesn't stretch. So basically the acceleration of all the particles attached to it will be equal. So light means we don't consider its weight, and the tension throughout the string will be the same. Inextensible means the acceleration of all particles attached to the string will be the same, and the smooth pulley means the tension on either side of the pulley will be the same, which is attached to the bottom of a rough plane. If the plane is rough, that means there's friction. We have to consider friction as the object A is moving along the plane. Inclined at an angle theta to the horizontal, where sine theta equals 0.6. Particle A lies on the plane, and particle B hangs vertically below the pulley, 0.25 meters above the horizontal ground. The string between A and the pulley B is parallel to the line of greatest slope of the plane. So what does that mean? It's parallel to the line of greatest slope of the plane. Basically what it means, if you, we'll just make a little diagram for those of you. Supposing you have the plane, which is, let me draw it in a bit of a more 3D way. So supposing you're looking at you're looking at this from this direction. You'll see in front of you like a ramp. Okay, and you'll see, this is the plane, this is inclined at angle theta. So there'll be basically a pulley at the end, and you have the object hanging down, B, and then you'll have the object A over here. So basically what it's saying is that this, this string that's got the object attached to it going down to the pulley is basically parallel to the greatest slope. So it's not at an angle like this or at an angle like that. That distance is basically the smallest distance between that point and the bottom of the ramp. It's kind of like, it's parallel to the slope of the plane. So it's not going to be coming down at an angle. It's going to come straight down from that point to that point. The shortest distance, you could say, perpendicular to the bottom of the plane, something like that. That's what it means by the line of greatest slope of the plane. That's what it means by that little statement, in case you didn't. It doesn't really affect the question, but sometimes it's good for you to have an understanding of what these things mean, because students get confused. What do they mean by this? So hopefully that gives you some sort of understanding. This is the coefficient of friction between A and the plane is 1.125. We know that friction, the maximum amount of friction that can be generated in a situation, is going to be equal to mu times R, where R is the reaction force, Mu is the coefficient of friction, which depends on the object, which is in the surface, depends on the surface, the roughness of the surface. Okay, so particle A is released from rest. Find the tension in the string and the magnitude of the acceleration of the particles. So now I'm going to put all this information that we have in the diagram down here so that we don't have to keep scrolling up and down to get to see what we need. So let's put all the information that we have got here. So they've told us about the masses. So therefore, you're going to have here the weight of particle A, which is going to be 0.2 times G. Now, as there might be some EdXL students watching, I'm going to just keep it in terms of G for now. If I was doing this as purely as a Cambridge student, then, because G is 10, you can write that as basically 2 newtons. And this is 3 newtons because G is 10, so 0.2 times 10 will be 2. And 0.3 times G is, times 10 is 3. I'll leave it in terms of G to make it more universal for those students who are also watching. And then we have the reaction force when the object is in contact with the surface. So I'll call this R. Then we have the friction, which is always opposing the motion. So when the object is released, A will slide down the plane and B will hit the ground, right? So it's going to friction is going to be this maximum value because it's going to slide down the plane and it's going to act opposite to the motion. And then, of course, we have the tension in the string. Okay, and if you consider B, it'll be acting upwards. Okay, and if you consider A, it's going to be acting down the plane because it's being pulled down. A is being pulled down by the mass of B. Right, so there's tension, and as we know, the tension is the same. And also, this is going to accelerate. There's an acceleration in this direction and this in this direction, and those two magnitudes of accelerations are the same. So the tensions have the same magnitude, the acceleration has the same magnitude. Okay, and so those are all the forces acting on the objects. All right, so what I'm going to do now is I'm going to make sure all the forces are resolved perpendicular and parallel to the plane. So I'm going to take this force over here, 0.2 G newtons. I'm going to resolve it. In the direction which is parallel to the plane. Let me just put that as a dotted line. And also perpendicular to the plane. Like that. Oops, it's supposed to be dotted. Okay. So we have this angle is theta. Okay, if this angle here is theta, this angle here will also be theta, and this can be understood from the concept from similar triangles. Okay, which I've gone through in another video as well. But basically, this triangle here, and you can say this big triangle here, are similar triangles. So some students they are confused about why are these two angles the same, and I'm just going to quickly explain why they're the same. Okay, you can think of these two triangles as being similar triangles, this triangle here and the whole triangle here. So we can see, for example, in this small triangle, okay, this angle is the same as the angle in this triangle. This is a shared angle, okay? And we can also see that in this big triangle, you have a right angle, and this small triangle, you also have a right angle. There's a right angle over here. This is vertical, this is horizontal. So both of these triangles, they have a right angle and this angle over here. So if we just draw it quickly, you have the big triangle like this. It has a right angle, okay, and it has this angle theta, and it has an angle here. Put it with 2 lines. Let's draw it with 2 lines. And then we have the small triangle that looks like this, and it has a right angle, and it has this angle with 2 lines. So these two angles are the same as these two. right? So by similarity, if two of the angles are the same, the third must be the same as the third as well, because add up to 180. That angle must be theta, right? So that's a little brief explanation of why we can call this angle theta without any problems. Not just assuming it's theta. We know from similarity that it is theta. Okay, that's one thing. And then secondly, when we want to resolve this force, I'm going to resolve this force here in the direction which is going into the angle. So let me just put another line here to make it clear. Okay, so if we want to take this, let me just arrange it 1 second. I'll just put it like this. Okay, now, if I want to resolve this force in the direction which is going into the angle this way, resolve this force in this direction, then I'm going to be going into the angle. So if I'm going into the angle, you're going to use always cosine. Okay, if you're going away from the angle given, you use sine. So I know that this force here is going to be 0.2g times cosine alpha, cosine theta, and this way it's going to be 0.2g times sine theta. Okay, so going into the angle given, I'm going to use cosine. Going away from the angle, I use sine. And what's the reason for that? Well, if we just join again a little line from here to here, okay, then we can see that this side is like, in this triangle, we form like a little right angle triangle here. This side is like the adjacent side, and this side is like the opposite side from that angle. So this is parallel to the plane, this is perpendicular to the plane. So that's going to be with cosine, and this side here, which is parallel to that, is going to be with sine. So this is going to be 0.2g cosine alpha, and this is going to be 0.2g times sine alpha. Okay, so I'm going into a bit of detail here just to make things hopefully a bit clearer for those students who don't understand where some of this stuff comes from. Okay, so hopefully that clears up a few things there. Right, so now what we're going to do is we are going to, let me just get rid of some of these things because they might be confusing for people afterwards. I don't need the angle there we're in. I don't need this line here. Okay, so basically now we're going to consider A and B, okay, and we're going to see, okay, we resolve the forces perpendicular to the plane for A. We'll have R is equal to 0.2g times cosine of theta, all right? It's not moving in this plane, which is perpendicular to the plane. It's not moving in that direction. So the acceleration there is 0. So the R is equal to 0.2 g cosine theta. And we know that from here that the sine of theta is 0.6. So the sine of theta is 0.6. Now, when you're given the sine of theta, you can find the cosine of theta very easily, which you will normally need. So what we can do is, if I make this into a fraction, I can say the sine of theta is like 6/10, which is 3/5. Now, if the sine of theta is 3/5, we can just think about Pythagoras' theorem here, because if this is theta, the sine of theta has a value of 3 opposite over 5 hypotenuse. So therefore, this is going to be 4 here, because by Pythagoras, if the hypotenuse is 5 and the one shorter side is 3, the other shorter side is going to be 4 by Pythagoras' theorem. So therefore, we're going to say that cosine theta, therefore, is going to be adjacent over hypotenuse, which is 4/5. Okay, so we can say that this is going to be 0.8. 4/5 is 0.8. So we can say here we're going to have R equals 0.2 times 10 times 0.8, which is going to give us 0.2 times 10 times 0.8. Messed up a bit there. Okay, so that's going to give us 8 over 5, which is 1.6 newtons. So R is 1.6 newtons. All right, so we found R. Okay, and we can now consider B. We're going to consider B by resolving forces going down the plane. So consider A. We're still considering A, but this time we're considering the forces going down the plane. We're resolving the forces down the plane, still with A. Okay, so down the plane, we can see here that we have down the plane, we have the tension, and we have plus the weight acting down, which is 0.2 g sine of theta, and we got minus the friction is now it's accelerating down the plane, so we're using the resultant force is equal to the mass times acceleration. So we got the mass of the object going down the plane, which is 0.2 times acceleration, which is A, which is one of the things we have to find. So we've got to find the tension and we've got to find the acceleration. So from here, we can work out a few things. Again, we know sine theta is 0.6, that's given to us. And we can work out what F max is now. So let's work out what F max is. Now F max, as we said, is equal to mu times R. And we found what R is, and we're told mu is 1.125. Mu is the coefficient of friction. So you got 1.125 times R, which is 1.6, and this will give us the value of F max. So we multiply this by 1.125. 1.125. Going on with my calculator here. 1.125. Okay, that gives us 9 over 5, which is 1.8. So that's 1.8 newtons. All right, so we can say, therefore, that T plus 0.2 times 10 times 0.6 minus 1.8 is equal to 0.2a. So let's work out what this is. We have 0.2 times 10 times 0.6 minus 1.8. That gives us negative 0.6. We can say T minus 0.6 is equal to 0.2a. So basically now we have an equation, okay, which we can use, which involves A. So T minus 0.6 equals 0.2a. Now if we consider the forces acting on the particle B, and as B is moving down, I'll take down as positive. I can say that the forces are the weight, which is 0.3 g, minus the tension, which is acting upwards. Something's moved around here. Okay, the tension, which is acting upwards. And we know that's equal to its mass, which is 0.3 times acceleration. So this is, again, the resultant force equals the mass times acceleration. So this is going to be 3 minus T equals 0.3a. So now we have two equations, which we can solve them simultaneously, and thereby we can find the value of T and A. So we have T minus 0.6 equals 0.2a, and we have 3 minus T equals 0.3a. So if these two equations, if we add them together, the T's will disappear because they have different signs. So you'll have T minus 0.6 plus 3 and plus minus T. T's will disappear. You'll end up with 3 minus 0.6 equals, and if you add these together, you get 0.5a. So what we've done here, we've added these two equations together to eliminate the T. Okay, so we've done 1 minus 2. Okay, so now, so 1 plus 2, we added them together to get rid of, they have different signs. So that gives us 2.4 equals 0.5a. So basically 24 equals 5a. So a is equal to 24 divided by 5, which is 4.8. 4.8 meters per second squared. So there's acceleration. Let me just make sure I didn't make any silly mistakes there with my calculation. So we have 3 minus 0.6. That's 2.4. That's right. And then we're going to divide that by 0.5. Which gives us 4.8. Good. All right. So we have now the acceleration. And now we've got to find the tension. So we got the magnitude of the acceleration is 4.8 meters per second squared. And we can use any of these two equations. I could use this one here. I can say T is equal to 0.2 times 4.8 plus 0.6. So we're going to use equation 1 to substitute A instead of 4.8 instead of A. And that should give us the tension. So we take the last answer, 4.8, multiply it by 0.2, and then add 0.6. Keep doing this. 0.6. That gives us 1.56 newtons, exactly 1.56 newtons. So there we have the tension, and there we have the acceleration. So we have answered part A of this question. Okay, now we're going to go on to part B. Now part B says, when B reaches the ground, it comes to rest. Okay, find the total distance that A travels down the plane from when it's released until it comes to rest. You may assume that A does not reach the pulley. So we could actually do this question in two ways. We could use the fact that there's friction acting, that when B reaches the ground, there's no tension in the string, there's new acceleration in the system, and we can work out the new acceleration, work out the speed of A as it was traveling down. Once B hit the ground, we can work out what speed it had reached, and then at that point, the acceleration will change, and it will start to slow down because the friction will probably decelerate as it says it's going to come to rest. And we can then work out how far, we can work out its new acceleration and work out therefore the distance it takes to come to rest, and then add that to the distance that it has moved before B hit the ground. Or we can use work energy principle, okay, which I'm going to show you both ways. Right? So first, let's get the diagram here. Okay, so now here I have the diagram that we had on the last page. I've taken out some of the unnecessary things that we don't need now, because basically what's going to happen now is this is going to move. Just say, B is going to hit the ground. When B hits the ground, okay, then the tension in the string is going to be gone. So you won't have any tension in the whole string. And it's like you have just this particle that's going down the plane. Okay, Fmax won't be changed because it's still moving, and the component of the weight will still be the same, okay, going down the plane. Right, so we already worked out Fmax. So I don't need to keep the R and stuff here because we worked out what Fmax is. This is Fmax. Okay, we've worked out that in the last part of the question. That won't change. Fmax will still be the same. It's still moving on the same plane, the same angle, same weight. Okay, so the Fmax won't change. And the component of the weight down the plane won't change. But what's going to change is there's no tension now in the string. So the tension's gone. Okay, so there's going to be new acceleration. Okay, that if we resolve the forces down the plane, we can find the acceleration. Now B's out of the picture, just hit the ground. So A moved from this point to this point. So it's moved so far 0.25 meters. And then at this point, the acceleration changes. Why? Because when B hits the ground, the string becomes slack. There's nothing pulling it down apart from its weight. So the acceleration now, its situation changes. Okay, so we need to work out what speed A reaches, or by the time it gets to that point. So let's do that as well. Let's work out that first. We can say the speed of A when string breaks, when the string becomes slack, or when B hits the ground. When B hits the ground. So the speed of A at the point when B hits the ground, well, we can see this is the original situation. So the original situation before was that if we use Suvat here, it's moved 0.25 meters. Its initial speed before was 0. Its final speed is what we want to find. The acceleration was 4.8 meters per second squared. And the time it took, we don't know. But we can see we can use v squared equals u squared plus 2as to work out this speed. So v squared is equal to 0 squared plus 2 times 4.8 times the distance 0.25. So this will give us what v squared is. So we got 2 times 4.8 times 0.25. That gives us 12 over 5, which is 2.4. Okay, so v is going to be the square root of 2.4. I'll leave it like this for now. I won't round it because we might need it. It's not a final answer. It's an exact form. Leave it in this exact form better. Okay, so that's the speed of A as it reaches this point. So it's going at 2.4 meters per second, the speed. Now, we're going to consider the change of the situation. I drew the diagram up here. We're supposed to answer under here, but I'm just doing it up there, no problem. So the change in situation now is what? Is that the acceleration is now going to change at this point. The acceleration now, if we consider A after B hits the ground. After B hits the ground. Okay. Okay, consider A after B hits the ground. Now the acceleration is going to change. So I'll do this down here. Okay, so after B hits the ground, what's going to happen is you've got the forces acting down, which is 0.2 g. So if we consider going down the plane, we've got 0.2 g, and we have minus 1.8. Minus 1.8 is equal to the mass, which is 0.2 times acceleration. So this is going to be 2 minus 1.8, which is going to be 0.2, okay, is equal to, 0.2 g sine theta. What I'm doing, sorry. Give me a second there, sorry. So it's 0.2 g times sine theta. Times sine theta, okay, minus F max, and that's equal to the mass, which is 0.2 times the acceleration. So sine theta is 0.6. So 0.2 times 10 times 0.6 minus 1.8 is equal to 0.2a. Okay, and therefore we're going to have have 0.2, again 0.2 times 10 times 0.6 minus 1.8, that's minus 3.5 divided by 0.2, that was minus 0.6 equals 0.2a, so a is going to be minus 3 meters per second squared. You get negative 0.6 and you divide it by 0.2, that gives you minus 3. So the acceleration is negative 3 meters per second squared. So now we have a new situation and we've got to find how far it moves down the plane, because it's going to come to rest, it's decelerating, and it says it's not going to reach the pulley, so it's going to come to rest before the pulley. So S is what we're trying to find. U was the speed with which it was moving at the point at which B hit the ground, which we worked out to be the square root of 2.4. In this case, that's the square root of 2.4. V is its speed when it comes to rest, which is 0. A is its new acceleration, which is negative 3, and time, I don't think we need it. Again, we can use v squared equals u squared plus 2as. So we know v is 0. So this is going to be 2.4, because when you square 2.4, you're going to get the root of 2.4, you're going to get 2.4. That's why I left it in that form, so it's more exact. Plus 2 times acceleration, which is minus 3, times s, which is what we have to find. So we can calculate this. You're going to have minus 2.4 over minus 6 equals s. So s is going to be 2.4 divided by 6, which gives you 0.4 meters. Okay, so therefore, the total distance is moved. Total distance, okay, after release. So that means right from the beginning, well, we know it's moved 0.25 meters and then a further 0.4 meters. So it's 0.25 plus 0.4. So this is before B hit the ground, and this is after B hit the ground. That gives you 0.65 meters, and that's the answer to question part B, and that completes this question. However, I did say that I'm going to explain how we can do this in a second way, which is using the work energy principle. Okay, so now I'm going to explain part B in a slightly different way using the work energy principle. Okay, so we're going to use the second method for part B, which is called the work energy principle. All right, so let's see how this works. Now, this might be useful for those students who will take M2 in Excel, in Cambridge. This is an M1 as well. So basically, the work energy principle states that the kinetic energy at the start, the initial, plus the potential energy at the start, which we call initial, plus the work coming in to the system, the work inside the system, work entering the system, should always be the same as the kinetic energy at the end, final, plus the potential energy at the end, plus the work going out of the system. Right, so that's called the work energy principle, and this will help you to answer any of these type of questions. So we've got to think about where this object is going to start. Let's say that B has already hit the ground. Okay, so I'll just draw this line here. Let's say that B has hit the ground already. All right, so B has hit the ground. We're taking it from that point onwards. So B has hit the ground. Okay, so it's already traveled this distance, 0.25 meters. So A has gone from somewhere up here to this point. It's traveled 0.25 meters. When it reached here, we know that its speed is going to be, as we already calculated. So this is something that you'd have to do first. You'd have to calculate its speed at that point when it reaches A, which we did, and we got root of 2.4. So we'll keep it in that form. So we got root of 2.4 meters per second. And we know that when it reaches, it doesn't reach the pulley, say it reaches this point over here. Okay, let's call this level X and Y, just to make it clear. So I'm going to call this level here, where it started, I'm going to call this X, and this level here, where it ends, I'm going to call it level Y. So this is level X, and this is level Y. So when it reaches level Y, okay, its speed is going to be equal to 0 meters per second, because it's got to come to rest. Okay, so we also got to think about, because we've got to deal with the potential energy, we've got to think about the vertical height that it moves through. So we've got to consider this height that it moves through. And what we're trying to find is this distance that it's moving along the plane. That's what we have to find. Let's call the X. Okay, remember this is a right angle. This is the same angle as this, which is theta. Okay, so now, if we use the work energy principle on this, in the beginning, it's kinetic energy. Remember, kinetic energy is a half mv squared, or we can say initial, it will be u squared in this case. Half mu squared plus mg times the height that it started off with, plus the work in, which we're going to discuss in a minute, equals the final kinetic energy, which is a half times m times its final speed squared plus mg and its height in the second situation plus the work that's gone out of the system. Okay, now putting the values in, we have a half times m times u squared, which is the original speed there. So we're going to have a half times the mass, which is 0.2 times u squared. Now this is u is root 2.4, so u squared is going to be 2.4 plus the mass, which is 0.2 times g, which is 10 times h. Now h1 is this distance here, and we want to try to express this in terms of x because we're trying to find x. So what we can do is we can use this right angle triangle that's formed here, and we can say, okay, this angle is theta. So we can say sine theta is equal to opposite over hypotenuse h1 over x. So that means h1 is going to be x times sine theta. So here we'll have x times sine theta, and we know that sine theta is equal to 0.6. So it's going to be basically 0.6 times x. I'll just put here 0.6x. Okay, so we can say therefore the height 1 is equal to 0.6x. So I'll put that in here as 0.6x. And then the work in, well, that's like any work that went into the system that added to the energy in the system, and there's no work that went into the system. Okay, in terms of going into the system, there's nothing, there's no driving force, anything like that. So that's going to be plus 0, and that's equal to, and when it reaches this point, which we call level y, at that point the speed is 0, and also its vertical height is 0 because we call that the 0 or the origin where potential energy is 0. So both of these will be 0. And then we have the work out. Now the work out is due to the friction. Okay, and the friction was 1.8 newtons. Now don't make the mistake of just putting 1.8 here. The work done is the force times the distance that it's moved through in that direction it moved. So the distance that the friction has been applied for, which is its work out, why? Because it's taken, it's slowing down the system. It's kind of like the energy going out of the system because of the frictional force. So that's why it's in the work out section. So frictional force, air resistance, these kind of things are in the work out section. Driving forces and such would be in the work in section. So it's 1.8 times the distance that is acting through. So it's acting through the distance that we have to find x. So it's 1.8 times x. Now, a big mistake that people make is if they just put the frictional force, they don't find the work done by the friction. We're finding the work done by the friction, which is its magnitude times the distance in the direction that it's been moving. So we don't use h, we use x because frictional force was working along this distance here, on that surface. And so that should give us the correct answer. So let's have a look. So we have half times 0.2 times 2.4. I think that's going to be 0.24 just to make sure. Half, which is 0.5 times 0.2 times 2.4. That gives you 6 over 25, which is 0.24. Plus, and we have 0.2 times 6, which is going to be 0.2 of 1.2. It's 1.2x. Just in case I've done something silly, just make sure. We have 0.2 times 10, which is 2 times 0.6, which should be 1.2. That's right. Okay, equals, and we have here 1.8x. So now we can subtract. So 1.8 minus 1.2, which is 0.6x, equals 0.24. So you have 0.24 divided by x. Sorry, divided by 0.6 gives us x. So therefore x is equal to, that's going to be 0.4, I think, as we should find. So we got 0.24. 0.24 divided by 0.6 gives us 2 over 5, which is 0.4, which is exactly what we were looking for. That's the distance x. So it's moved, therefore the total distance we're looking for is going to be 0.25, the distance it moved while B was still attached to the string, or before B hit the ground, plus 0.4 meters, which is the distance is moved after B has hit the ground. There's no tension in the string. That gives you 0.65 meters. So that's exactly the same answer that we got previously. Okay, so that's an alternative way of answering this part B of the question by using the work energy principle. Okay, so I know this is a very long video, but I try to go through things in detail. I'm not making these videos to tell you how long you should take to answer the question. Rather, I'm using these videos to try to explain the concepts in a bit more detail rather than just being a talking marking scheme. So there's basically the answer for this whole question. I hope that was clear. Other questions from this paper can be found in the playlist that will appear on the top right of the screen at the end of this video. Other questions from the topic of inclined planes you can find in the playlist over here. Other questions dealing with work energy principle you can find in the playlist over here. You can subscribe to my channel by clicking on the link at the top. Thank you for watching and see you soon.